Our final project is going to talk about the fraud detection for a credit card. For our database, we have 1 million transactions with around like 8.7% of fraud rate, and we do that through like say 11 steps. And our final goal is to have the AUC and the precision scores with one point. And here's a data overview of the dataset about our dataset with 1 million transactions and 91% of normal data with 8.7% of fraud data. And the imbalance ratio is 10.44 to 1. And it has seven features comes originally with this dataset, and additionally like 7 engineering features we generated to make it easier for us to analyze with 0 missing values, so this data is slightly clean for us. And as for the features, it includes something like the median price ratio to the median price, which means like well, compared to its historical like purchase price, and it has information about distance from home to the transaction place, and if it's online order or not, if it use PIN number or not, if it use chips or not, if it's and the distance from the last transaction to the current place, and if it repeats the retailer or not. And the reason why we choose this dataset, because first of all, it's the scale and realism. It has 1 million transactions. It's large enough for us to stress test our models and validate the statistical significance at production scale. And it has rich features that we need, such as continuous features like distance and ratio, and binary features like whether it has chips or not, has PIN or not, or if it's online or not, which is similar our real-world card transaction system. Besides that, it's also like an open exercise, which is fully free on the open machine learning website and fully reproducible research with no data privacy constraints. And last but not the least, since credit card fraud costs like 33 billions annually worldwide, so it's really a serious problem, and that means like it's important to use like machine learning improvements to kind of improve the financial impact. And before analysis, we have some like hypotheses like certain behavioral features can drive the fraud, such as online purchase and purchase ratio anomalies and distance specs would be a strong like predictor rather than the authentication flags alone. And also we want to see like compared to the models, like if the nonlinear interactions would be benefit more than the linear regression like logistic regression. Besides that, we want to see like the ensemble add values would push beyond the single one, and the engineering beats any raw features, like the interaction with online ratio or better than the feature itself. As for the outcomes, we expect the target AUC ROC to greater than 9.5 and 0.95, and the target recall value is greater than 85%. So we want to qualify like which feature have the highest predictive power via sharp analysis, and we want to compare the different like models from linear tree boosting to neural network to see like which one performs best, and we deliver the 11 step end to end from raw data to the final deployment logic. And as for the data cleaning, first of all, we do the data cleaning. As for the data cleaning, we first the ARFF format, we align those column names, we typecasting, duplicate checks, and detect any outliers. We split the data into like 80 and 20% train and test groups, and we scale the data. And since the class is since the data kind of like imbalance, we auto adjust it with in the sklearn models. Also with XGBoost, we use scale pulse weight and SMOTE oversampling and threshold tuning to kind of like counteract with imbalance. And then we start doing the EDA. So first of all, we have the bar chart, like compared to the normal and fraud data. We can tell like almost like 91% of the transactions are normal and only like 8.7% are fraud, which kind of like makes sense to the real life. And as for the fraud rate, we can notice like the online order has a really high fraud rate compared to the other orders. And we notice like if we use PIN, it's the fraud rate will drops a lot. And if we use chips, the fraud rate also drops, which means like such ways can be a good like tools to avoid any fraud. And as for the continuous feature EDA, we check for the distance from home to the transaction place. It looks all normal until like for distance of more than like 200 kilometers, the fraud rate increased dramatically to like 44% of fraud, which makes sense. Like when the transaction happens far from your normal neighborhood, it's very likely to be something happened to the fraud, something like not made transaction by yourself. And as for the fraud rate by the purchase ratio, we can see if the purchase ratio is 5 times the normal purchase, it's like very low likely to be the fraud, which makes sense. Like if the transaction behavior doesn't similar to your normal transaction, then it's very likely to be a fraud made by somebody else. And as for the feature correlation heat map, we can notice like there's a strong correlation with the fraud and the purchase ratio, almost like 0.46, which means like purchase ratio can be some significant identifier. And also something like if it's online transaction also involves like 0.1 0.19% to the fraud, which could also be something need to notice. In addition, also the distance to the home can also be a very key identifier. So keep those in mind. We then start working on the feature engineering. Besides the 7 feature comes with this dataset, we create additional like 7 features. First of all, like the log distance to the home, which reduce the red skewness, improve the linear model performance. And we log the distance to the last transaction, also reduce the red skewness. And also we have the distance ratio, which is location to make the location consistent. Also, we create a new feature like price anomaly to decide to binary flag any fraud transactions more than 3 ratios, and also something like digital footprint to decide like if card not present, what's the risk score, and also we include the security scores to us to show the authentication strengths. And we also use the online times ratio to capture the high value online fraud. And first of all, we imply the linear model as our baseline. We use it because it's the most basic model we have in our mind, and we train it really fast. It can show the feature direction and magnitude. It's kind of a baseline, which means all the later models should perform better, at least better than this one. And as it turns out, the linear model achieves the AUC ROC to to 98%, and the F1 score to 75%, 0.75, and precision 0.65, recall 0.96. And we save this as our baseline, and we expect later models perform better than this. And then we apply the tree and boosting models. Be more specific, we use the random forest, XGBoost, light GBM, and gradient boosting, and we perform all those models and compare their AUC, F1, and recall scores to see which one performs better. As it turns out, the gradient boosting performs the best with 1 AUC and 0.99 F1 and 0.99 recall values. And after that, we try to imply the neural network with input the 14 features we have. And the first hidden layer we have like 256 neurons, and we apply batch norm, ReLU, and drop out the value to 0.3. And then we go to the second hidden layer with 128 neurons. We go to the same process, batch norm and ReLU. And the third hidden layer with 64 neurons like input. And as for the output, we have 1 neuron's output with sigmoid and go get the final fraud probability with best AUC 1 and the F1 score, best F1 score 0.94, and the recall value like 19.99%, 99%, and which performed quite well. And as for the configuration, we use BCE with Logis laws, and the optimizer we use Adam, and for scheduler we reduce plateau. As for the imbalance, we use SMOTE oversampling, minority of the class, and for the device we use T4 GPU with 2048 batch 30 epochs. And then we try to find the threshold optimization through the precise and recall curve. Through that, we want to find the best F1 scores and recall scores. It turns out we find the threshold at 0.906 with F1 scores 0.99 and recall like 0.9993 with the weighted cost 1,1578. And it turns out the best module we select is gradient boosting with AUC 1 and F1 0.996 with recall 0.993 and has the lowest weighted cost with only 490. So as it turns out, we present the result in the confusion matrix with the normal values like almost 18, I don't know, like 0.18 like millions and 17,000 like fraud value with only 49 false negative, which performs quite well. And finally, we apply the sharp analysis, shape analysis to decide like which features involves most in predicting the fraud transaction. It turns out, like not surprisingly, the ratio to median purchase price involves the most to predict the fraud feature. And also the online transaction together with the ratio become the second important. The third one is distance from home. And as for the PIN number, it can be the negative shape, which means it can decrease the chance of the fraud happening. So besides that, has come to the conclusion. The feature engineer, it turns out like the feature engineering wins with ratio to median dominates. Then 26.7% shape, above like 5 times median carrier fraud rate. And the engineered online times ratio ranked number 2 outperforms every original like raw features. And the price anomaly flag provides a simple and auditable row-based signal. As for the model selection and thread, it turns out like the gradient boosting is the best model with the lowest weighted cost, only like 490 on 200k test transactions, and the threshold like 0.906 maximizes the F1 score at 0.9917. Default 0.5 is inappropriate for imbalanced data. And as for the neural network, with AUC1 achieved equal accuracy but has a higher operational cost. And when it comes to the explainability and auto machine learning gap, the SHAP tree explainer delivers per like prediction attribution mandatory for regularly audit trails. And auto machine learning cannot construct interaction terms or like tune the cost sensitive thread. Stacking ensemble adds 0 AUC but improves F1 to 0.9889 marginal infrastructure cost. And finally, it comes to the recommendation, the production deployment. We can replace the synthetic. We replace with synthetic data. We train on the real labeled transactions. Establish a data holdout set from production before any deployment decisions. And we can add time step based features such as transaction per hour and transactions more than like 500 kilometers. And we can deploy like cost calibrated thresholds, set decision threshold based on actual false negative and false positive cost ratio from the fraud operation team. And we may also log the per prediction shape values to avoid any like rescues. As for the future work, we mainly deploy the PSI-based drift monitoring, and we can use the graph neural networks as the graph to capture the ring fraud patterns invisible to tabular models, and we can do the online learning by replace batch retraining with incremental learning such as the river framework. And we can ensemble real-time model updates as fraud pattern evolve without waiting for a monthly retraining cycle. Finally, we can use auto machine learning for initial hyperparameter search, then like layer custom interaction features and cost-sensitive threshold turning on top. Best of both approach works. So that's the end of the presentation. Thanks for watching.